integrand, because we all know the main theme was that we have to replace our integrand by a polynomial, and as we vary the degree of the polynomial, we will develop different methods. So the first method, which is trapezoidal, based on the concept that the integrand will be replaced by a degree 1 polynomial. Now this is a different method, let's say method number 2, and we call it Simpsons Simpsons 1/3. Yes, its name is like that, 1/3 rule. There are two Simpsons method. Method number 3 is also Simpsons. So just to distinguish between them, we use 1/3 or other parameter as whenever I explain to you the method number 3. So Simpsons 1/3 rule. What does this method do? It is a quite simple idea. For example, this integrand is given to you a to b f of x dx, and whenever the integrand is given to us, we want to apply the integration on integral on that part. Okay, so our theme was that our function f of x will be replaced by a polynomial of suitable degrees. Theme will be the same. So in Simpson 1/3 rule, what we do, we will replace it our integrand for the same length of integration by a polynomial of suitable degree, and in this case the suitable degree is degree 2 for Simpson 1/3 rule. Theme is same. Theme is that you have to replace your integrand by a polynomial of suitable degree. However, the degree in this case is 2, degree 2. So if you are talking about Simpson 1/3 as compared to trapezoidal, the main difference is that you have to replace the integrand by a polynomial of degree 2. That is a quadratic function. Polynomial degree 2 means quadratic function, or geometrically you all know that function usually they are described like that. For example, p2x can be written as ax square bx plus c, something like that. Okay, so this is your quadratic. So you replace your integrand by polynomial degree 2 and you can integrate, but for every integrand you have to compute a b c uniquely, so that you can say that okay, our integrand represents this our integrand is represented by this polynomial. But that's a tricky business. Let's understand the concept in geometrically. For example, also we do not have to drive this thing, but concept is very important as an engineering student. So for example, if this is the domain a to b and this is our integrand, I usually draw it like that. That is, what do you mean by the integrand? That is, this is the graph of the function f of x. Same reason, we cannot integrate it, but we can plot it. So we have plotted using this graph. For example, this is the graph. So concept says that rather than using that function to interpolate or find the answer, you have to replace that by any other polynomial of suitable degree. For example, student, let's say with blue color, I am representing a polynomial of degree 2, but such that it must pass through the endpoint. That is the condition. So it is passing through, and I replace it with the degree 2 polynomial. So this blue function is basically a polynomial of degree 2. The question is still missing that how we will find that polynomial, but let's assume geometrically that if I have managed to find this polynomial, then what I'm doing now, I will not integrate anything beneath this white curve anymore. I will integrate beneath the blue curve, and my concept was that our integrand has been replaced by a polynomial degree 2. So if I manage to find the area beneath that curve, then that area approximately represent the area beneath this white curve, which is not in this case because the rough diagram, but that's the concept. Concept is you do not use the original integrand, you use the integrand that replaces by a polynomial of certain degree. In Simpson 1/3, you replaces by a polynomial of degree 2. So that's the main geometrical concept. Now the question is, how do we do that? Because for trapezoidal, when we replace it by a straight line, we apply the formula of trapezoid, and we will get the answer. But for degree 2, it is not the same. A degree 2 function could be of different shape and sizes. So how do we handle this thing? Okay, so the idea is like that. So theme is same. We have to replace it by a certain polynomial. But question is how we can do that. That's the main point. If we have any function, how do we fit that function of degree 2? So keep in mind that degree 2 function has three unknowns, a, b, and c, respective to this integrand. So if I can find a, b, c properly, then I can find the degree 2 polynomial. That's the main theme behind it. How we will do that, I will just explain you a little bit part of it. We do not need to drive this thing, we will use the direct relation, but the main theme must be clear. That is the mandatory part. So the idea is, let me select the white color again. So for example, if I want to fit a data by a polynomial of degree 2, so y, x, and the degree 2 polynomial. So we know that there are three unknowns. So that's so from the graph it is quite clear that what I want to do here, if you see clearly, I want to make sure that whether I put a in a given integrand, that is f of x, or in a polynomial, answer should be the same. So you can see that the nodes at the end at the lower limit and the upper limit are matching. This is the condition. So what I want to impose a condition that I want to find a quadratic function such that its lower limit, its answer at the lower limit matches the value of the integrand, and also the lower at the upper limit it also matches the integrand. In between, if it is matches precisely, that's a good thing, but it's usually not happen because every white function, that is the integrand, is not like a quadratic function. So if it is a quadratic, it will exactly matches, but it's not necessary all the time. So our idea was to replace it. This means that we need one more point to find that unknown, because there are three unknowns. So I need three conditions. I have two conditions which says that a at point a, that is a lower limit value of the integrand and a polynomial must be same. As the function of integrand is known to us, so I can compute the value of the function at this point. Similarly, at b, the value is f of b. It is also possible, but in between there is no relation available. But what I know that I can select any point from a to b, let's say, because all the x's are between a and b, any point. So for example, in Simpson one-third rule for our ease, what we do, we select the midpoint. So if I select the midpoint of this interval, then this coordinate is basically, let's call it c. This midpoint is equal to numerically a plus b by 2. This is the midpoint. So if I try to read our integrand at f of c, that would be here, f of c. And if I try to put this point c in the polynomial, that would be somewhere there. So there is a difference between these two. But how do we use this condition to find the polynomial? That's the main point. So what we are doing now, I am enforcing that my function will be behaved like that. What's the condition? Is that condition is like that. We have a, we have a b. I am trying to make similar y function here, if I can copy it properly. But now, now the polynomial, this is f of x. This is y equal to f of x. Okay. Now the where is that? Let's say let's select red color. So let's do it again with the blue to avoid confusion. So what I'm doing now, so I want to make sure that my missing polynomial matches this point, and there is another point c which also matches. So let's say this is a called quadratic function that I fit, just for understanding. It does not look like a quadratic, but let's assume this is a quadratic. So I'm enforcing now that I want to find a quadratic function that makes sure that it will match at lower limit, it will match the upper limit integrand, and also there is another point c which is equal to a plus b by 2. So this has to match. This is the whole story of this problem. So how do we handle this thing, or how do we compute the, it is not a straight line, keep in mind it is some sort of a curve. So I want to make sure that whatever the area will get will. So idea is that our unknown polynomial which is not known must match the data with the exact at least at 3 points. That is our requirement. So how do we write down this thing in mathematically? So mathematically we will write down the condition like that. I'm just giving the idea that how do we compute this polynomial, because the theme is replace your integrand by the polynomial of suitable degree that reflects this integrand property. Once you have that condition, I mean you have an equation. For example, let's assume you know ABC. Okay, one thing I want to highlight is that these ABC, these AB has nothing to do with this AB. Okay, they are different ABs and they are different. Let me make it like that. Rather than calling it AB, let's call it to avoid confusion only. So let's call them like that. Let's call it C2, C1 and C0. Let's call it like that. Okay, the coefficients of x square is C2. Let me write down again. Let's say I want to find the polynomial of degree 2, which is like defined like that. C2 x square C1x plus C0. I can use the same thing as well, but in that case, the problem we have is that student may be confused that this AB has to be the same as this AB. No, it's not like that. If it's like that, life is easy. But no. Now come back to the main point. So what we are saying, we want to find a polynomial of degree 2, which is the requirement of the Simpson 1/3 method, but in such a way that it matches the values of the function at 3 points: lower limit, upper limit, and as well as the some arbitrary chosen point, which is the midpoint of this interval. It also matches. So we have this condition. So what we want to do, we want to match the condition. So what we are saying, if I put in degree 2 polynomial value a, what does mean, instead of x I want to put a. So if I put a, it has to match the value of the function, that is f of a. So if I put here, I will get C2 a square, a is known quantity, C1 a, C0, and they all have to be equal to f of a. So this f of x is given to us. It is an integrand. So I need to put the lower limit there. So I will get the answer. The second condition that I will obtain is by using this condition. F p of 2 at b. So C2, I will replace wherever x is by b2. B square, C1b, C0. And this must be equal to the value of the integrand at the lower limit. Upper limit. So this is the upper limit. And the third condition will be obtained using this midpoint. So what I want to say, if I put C2 instead of x, I will put C point here. So I must get C square plus C1c C0, and this must be equal to f of c. So here the right hand side is f of a, f of b, f of c, and the left hand side, the unknowns are C1, C2, C0. I don't know these unknowns. If I know these unknowns, then life is easy. I will just replace this unknown in the place of C2, C1, C0 respectively. In that way, I will know the what I will know. I will know the polynomial, and then I will replace the polynomial here, and I will integrate the polynomial from a to b, which is most easiest thing, because integrating a polynomial is easy. It will be x cube over 3, x square over 2, and x, and upper limit minus. I will get the answer easy. So question is, how do we find the only thing that is missing is C2, C1, and C0 coefficients. But I have a 3 conditions now, and I have a 3 unknowns. So whenever we have 3 conditions and 3 unknowns, we can solve it using a matrix. So we can find the value of C0, C1, and C2, and I will replace them on this part. Okay. We do not have to solve. I already told you this is not a part of the solution strategy, but we can solve them as well. Okay. So when you ever solve it, we can solve it like that. If you are still interested to know, the idea is quite simple. The first equation is C2 a square a naught a1. So the first equation is like that: a square a1, b square b1, c square c1. This is the matrix. They all are known to us. A, B, C are known. A are lower limit, B are lower limit, and C is the midpoint of upper and lower limit. So they all are known. This is the matrix, and the unknowns are C2, C1, C0. They are unknown, and the right hand side is also known to us. Right hand sides are f of a, that is the integrand read it at read at so not read at the point a, integrand which is read at point b, and integrand which is read at the midpoint, that is c. So I have a 3 points. So this is known to me. This is the matrix. This is the right hand side known. I need to find the inverse of the matrix. So I will get C2, C1, C3. Let's assume we get C0, C1, and C2. Let's assume that we know these values. So if we do not need to compute, we can repeat this process for any integrand, and we will get the, by inverting this 3 by 3. You can use a calculator, anything to do so. But we do not need to do. We will have a compact notation to work with this type of problem. So let's say C0, C1, and C2 are known to us. This is not anymore unknown. So when we know that, what we can do, we can find the polynomial exactly that represent our integrand to certain degree of 2. So what would be the, if C0, C2, C1 are unknown to me, then I will replace them here on this one. So if I replace it, I will get C2 x square, C1 x, and C0. Now C2, C1, C0, C1, C2 all are known to us. Are known to us by solving above matrix. So I'm not including the solution, but if you want, you can know how I got this idea. You know the idea. So if it is known to me, then what I can do, I can simply reuse the concept. Concept says you have to replace your integrand, this f of x dx, by a polynomial of suitable degree. So here the suitable degree in Simpson one third rule is degree 2. So degree 2 would be defined like that: a to b c1x c0 dx. We do not need to integrate, but we know that now this is known to us. So we can integrate them minus upper limit and lower limit, and the values of C0, C1 which will be obtained from it, I can replace them. And after the simplification of this whole process, you need to solve, like what you have to do, the values that you will obtain from C0, C1, C2 will be replaced here. And when it will be replaced, you have to integrate, that is, this will become x cube over 3, x square over 2, x will be there, and then you have to subtract upper limit minus lower limit. You will get a definite answer. Definite answer means it is not a function of x anymore, it will be a numerical quantity. So let's say after the simplification, we do not need to show the step. The only thing we have to use that after solving, so integrand is replaced by polynomial degree 2, so I'm using approximation. But if I solve this thing, I will get the exact answer. Exact answer is equal to, and the answer that I will get after doing two step, what I will replace C0, C1, C2 in this form. Here they are complicated, and then integrating from A to B. That is integration. Normally polynomial we can integrate easily, and then subtracting upper limit minus lower limit. So final answer after making all the simplifications, you will get this answer. You will get the following answer: d minus a upon 3 times of, and you just need to know this final answer. That's enough as engineering student. So but from where it comes, it is not a random, there is a logic behind it, but I want to avoid that mathematical derivation. So f of a for you, f of a plus the other part that we have here is quite simple: 4 times f of c. I know you all remember what is c. C is the midpoint. Is this one, this is the c. C is, and it's not that difficult to compute c, just to take the midpoint of upper and lower limit, a plus b by 2 plus f of c, f of b, sorry, f of b. So this is how you obtain. So one can clearly see it not depending on x. This will give you a numerical answer. That will be a number. So the idea is let's connect the story again. Integrand is replaced by polynomial degree 2. Polynomial degree 2 is defined like that. but we need to find a polynomial such that it matches the integrand at three different points. So upper and lower limit are always necessary. In between points are up to us. So for Simpson one-third rule, we set the and for our ease we set the point equal to midpoint of this domain. Okay, so this is the midpoint. So we try to match the point. Now we are not sure the blue curve will match the white curve entirely. It is possible as well if the white and white curve is a quadratic, but if not, then it will at least match the white curve or a blue curve at the 3 points: lower limit, upper limit, and the midpoint. This gives us three conditions, and these conditions will help leads to a matrix of 3 by 3, and where C0, C1, C2 they are unknown, and this is known to us, and this is known to us. So we will replace it, like we solve it. We do not need to show, but we can solve it this thing, and we will get C2, C1, C0. So this is the same polynomial as the last slide, but when we have this thing, it means that, what does this mean? That C2, C1, C0 are known to us. We replace it, we integrate it, and when we integrate it, let's say the final answer is exactly defined like this. So what does this mean? What does this represent? So this represents the area under polynomial of degree 2. That is blue curve. If you go on a previous slide, so that equation gives the area under this blue curve. Okay, so you just need to keep in mind that this will be. But what's the reason behind it? How I got this? Obviously, we will not go it in a one step. It needs some 2 or 3 slides of simplifications, and then you will reach to that part. But you have to memorize, or you should know that this is the final answer. What does it reflect? This reflects the area under the polynomial of degree 2. Keep in mind, because I integrated polynomial of degree 2, it does not reflect the area beneath the white curve. That is the integrand. Keep in mind that. But we are saying this is approximately equal, so that's okay. Okay, so student, so what I have now, so if I want to apply for I have to cover both methods, so I'm little bit fast as well. So Simpson's one-third rule, what we have, if I want to integrate f of x dx, so that would be approximately equal to f of a plus 4 times of f of c, that is a midpoint, plus f of b, and this whole is multiplying by, I'm writing that term letter, b minus a times of 3. So student, now you understand why it is called one-third, because this 1/3 factor will be taken out as a common. It can be taken out common. So one-third. Just to distinguish, there is another Simpson method as well, which is called 3 by 8. In that, the 3 or by 8 can be taken out as a common. So they want to distinguish them. So this is the main idea. Okay. So I hope you understand the one. Now the same point is that this is what we applied over a whole domain. Is there any way that we can apply in a let's say in easiest way, the or to have a much more accuracy? So we will use a composite Simpson one-third rule. And whenever I told you already at the time of trapezoidal rule, so whenever you say composite, this means that does not have, and this does not mean that you are talking about some new method. It is the same method. Method is this one. And what's that method says? You have to replace your integrand by a polynomial of degree 2. So when you do that, you are talking about Simpson one-third. This is the method. This is the rule. And but in composite sense, what we do nothing. We just divide the domain into a small pieces, and we will try to repeat the process in a data set, so that we can have a much more accuracy. Because the concept is, if you apply a scheme over a whole domain A to B, that will generate error larger as compared to if you repeat that process in a small chunks and then add up together, so that your error will be minimized. That's the main idea. So idea, what is the idea now? Is nothing. I'm not going to explain the detail again, but you all know that if Let me write it down a little bit larger. So if it is starting from A, ending at somewhere B, X and Y. So what I'm going to do now, I will divide my or this is the integrand, for example. So what I'm going to do now, I am dividing that domain into small pieces. So you remember I used to call the first data lower limit x naught and the last one xn, and calling it xn has a reason. The reason is that I want to divide the data set into n. Let me check it whether I use a small n or capital N. Capital N. I use the symbol capital N. So which means that this would be a capital N then, where if you remember the capital N represents number of intervals. This is in our hand, how many intervals we want. And the idea is h, which is the width of the interval, is equal to upper limit minus lower limit divided by number of intervals. So you can compute width of the interval. So x naught is the first data, the second data is x1, the third is x2, third is x4, x5, x6, and so on till something last value. So last is xn, second last is xn minus 1 and xn minus 2. This was the last one. Okay, so the first value. So this is the x naught. I can, and this is my integrand, the given function. This is f of x. So I can put x naught in this function. So I will get some value y naught. If I put x1 there, I will get some y1. If I put x2, oh, I forgot to mention x3. X naught, x1, x2, x3. This is x4, x5. Okay, and then it will continue till the second last and last. Okay, so x2, this is y1, this is y2, and then there is some like y3, this is y4, and then let's say y5. Then you continue, and in the second last, you will get y n minus 1, and the last value is yn, and the third last we need here. So let's call it yn minus 2. Okay, so this is how we define. And then the concept was that we have to divide them into chunks. But I can divide it like that. But what I am doing now, I am dividing in the pair of two intervals. These two intervals, this one interval 1, interval 2 are combined together. You can understand clearly. Our idea was to replace this whole integrand by a polynomial of degree 2. And to replace a polynomial of degree 2, I need 3 points. So I cannot replace between the 2 points. I need 3 points. So what I'm doing now, the data x in the interval, I am using this as an A, this as a B, and this point as a C, which is obviously a midpoint of these two. Okay, so I'm making a pair of two intervals. In Simpson 1/3, we make a pair of two intervals. The data is there in between, that's necessary. And similarly, we will have some y6 as well. And in last, we have this data defined. Okay, so I mean, I do not want to draw the middle line. Okay, so this is not the part. Okay, so this is one. So what is this region? It's called one panel. Okay, this is called panel. And one panel is equal to two intervals. In Simpsons 1/3, in trapezoidal it is one panel equal to one interval. In Simpsons, I have two intervals there, x0 to x1 and x1 to x2, but I'm combining these two intervals and treating that as a one unit. That one unit is called one panel. So this is second panel, third panel, fourth panel, and so on. Okay, so I'm combining two intervals to make a one panel. So to distinguish, then I'm using a one different color so that you can understand what I mean. If I I am drawing this means that I am combining these two panels, these two intervals. Similarly, in between these two, so this is one panel, this other panel. Similarly, if I continue till the last, I will get other panel. Okay, so two intervals equal to one panel, two intervals equal to one panel, and so on. So this is the requirement. So student, one panel, two intervals. So why? Because I know that I have to apply Simpson's one-third rule. So for Simpson one-third rule, I need 3 points. So two panel give me 3 points, and I can apply Simpson one-third rule in this interval, then in this interval, and this interval, and the last interval, and then I will add up all of them so that I will get this blue shaded areas in each panel. So that's the main theme. Okay, main idea, not a theme. That's the idea. So how do we do that? Very simple, student. Now what we have to do, we have just developed a formula. This formula is valid for a whole domain. When the first value starts at A, ends at B, then you have to use this thing. One thing I mentioned to point out that each interval has a length h. Okay, so this n is a number of intervals, not panels, number of intervals. They like this 1, 2, 3, 4, 5, 6, like this. Okay, so they are the number of intervals, but to implement one-third, we need to combine, we need to consider two intervals together to have a one panel, and each panel I will apply Simpson one-third rule. So I'm going to apply Simpson one-third in this panel, I will going to apply Simpson one-third in this panel, and I will going to apply Simpson one-third in this panel. So in this way, I will get the area under this panel, each panel, and that I will sum up all the areas. So this will give me the area 1, this will give me the area 2, and this will give me the area whatever. I know this is n by 2. Okay, so why n by 2? Instead, one thing you have to keep in mind that if I have to cover the entire domain by dividing the intervals in such a way that then I have to combine two intervals and the domain will be covered completely. So this is only possible when n is a even. If n is not even numbers, then I cannot cover the domain. For example, if n is 15, let's make it easy. Let's n is 5. If n is 5, then two intervals will be used to form one panel. 3 and 4 will be used to form the second panel. One interval will be left vacant. So in Simpson one-third rule, there is a important point that you have to keep in mind, that n number of intervals, n must be even. Okay, keep in mind this point. Okay, student, if anyone of you like to have a break, can take it. There is no need to watch the lecture and complete one session. I am repeating it many times. Okay, so let's continue then after the break. So n must be even. That's the main point, student. This is the key crunch. If you do not do that, it will cause a problem. Okay, so I have to apply this general rule of Simpson one-third in each panel. So for first panel, that is A1, y0 will be f of a, y1, which is the midpoint of these two, will be f of c, and y2 will be f of b, and this will be multiplied by the starting and the ending. Okay, so what we have to do, we have to multiply it by the h, we have to multiply it by h. This b minus a is the limit. Okay, so but to apply that formula I need to combine them, so I'm combining it. So I have to do it like that, x2 minus this quantity, but that is regarded as a h, 1h, we are applying it h over 3. Here the h is interval is this. Let me explain to you from the previous diagram. So this is this quantity b minus a divided by this quantity, so this separation is basically h. Okay, so we use b minus a in that case. but it is h amount. Just keep in mind that this b minus a will be replaced by h here. So how do we do that? It is very simple problem, simple strategy. We will replace it by h. So if I apply it in the first interval, I have y0, y1, y2, add it like that, multiply by h over 3. Then in second interval, I have y2, y3, y4, where y2 will be behave like f of a, y3 will be behave like f of c, and y4 will be behave like uh, like this quantity. Okay, this is the main part. One thing, student, I want to clarify why this thing. There is one mistake I just noticed. It is in my back of mind. Student, there is no this quantity b minus a here reflect the total length of the interval. But the correct formula was b minus a divided by 6. The correct formula is b minus a divided by 6, not 3. And I will explain you why the 3 will come later stage. Okay, so this is basically b minus a divided by 6. Okay, so this is the correction. I will explain to you. I just recall it. It's a correction here. So now I want to apply this formula. Rest is same. So I want to apply this thing on this structure. So when I'm going to apply this thing, so this will become a, it also a as well, and this will be x2 will become b. So x2 minus x naught is 2 times of h. So I have to put 2 times of h here. So when I put 2 times of h, that 2 or 6 will be cancelled out and I will get h here. So when I want to move to h here, I will do it like that. But at the moment, this is the whole interval in the composite sense. So we are applying it in a composite sense. Composite sense is nothing, it's just an application of the same rule in a small segment. So the first segment is this one. So I'm going to apply it now. This implies integral a to b f of x the dx is approximately equal to a1, a2, a3 till whatever be the number of intervals are. When we make them combined together, the last interval must have an index 10. For example, if there are 10 intervals, because interval must be even, so if 10 intervals, then you will have 5 panels. So 5 panels means 10 divided by 2. So this is how the last number represent the number of panels in Simpson's 1/3 rule. For every rule, there is a different strategy. So A1. So A1 in this case is equal to A1 is the area of the first panel. This one, using in a Simpson sense, Simpson 1/3 rule. So the rule is, so the length of the interval in this case, let me explain this part. So if I subtract x2 minus x0, the length will be 2h. Okay, 2h. So what I have, b minus a, we have 2h divided by 6. F of a will become y0 plus 4 times of f of c, which is a midpoint. Midpoint in this case will be the y1, and the end point, that is set to y2. So this is just a a1.